Okay, continuing with practice test number 2 for Chapter 7 test. We are on problem number 8, and in this problem, you are being given some information about an angle that's between 0 and 2 pi, and they're asking you to find the exact value of the indicated trig function. So ultimately, you want to be able to find the cosine of a double angle. But this information is for you to set up your triangle. Okay, so unlike some of the other problems that were in this test, you are being indirectly told which quadrant to spin to. You know that it's somewhere between 0 and 2 pi, but that's not quite good enough. Usually you're told, hey, spin between pi over 2 and 1 pi, so you know exactly which quadrant you're in. Here you are being told, but you have to think in a more abstract sense. So this little piece of information that you have right here, that the tan is negative. That's what it means for something to be less than 0. You know that the tan is negative. You know that the sine is positive. So you might consider using the saying, all students take calculus, which is introduced in Chapter 6, and probably have heard it before in some of your other math classes. Specifically, they would mention it in a geometry class, but here it goes. The word all means all 6 trig functions, sine, cosine, tangent, cotangent, etc. All 6 trig functions are positive. The word students, now you go by the first letter. Once you get past quadrant 1, you go by the first letter of each word. So it's all students take calculus. So the first letter reminds us of the trig function sine. So therefore sine is positive, and also cosecant is positive. And that's because cosecant is made up of nothing more than sine, so it would have to be positive also. Now I would continue with this with the all students take calculus, but I've already discovered the quadrant that I need to be in. Here the sine is positive, just like what you see right here. You were given a positive value for sine, and the tan is negative. Why is the tan negative here? Because these are the only 2 things that are positive. It refers to the trig functions that are positive. So if only sine and cosecant are positive here, that must mean that everything else, tan being one of them, would have to be negative. So you already found exactly what you're looking for. But if you do need to be in some other quadrant, because I'm not going to give you the same exact problem, it will go all students take, okay, again, use the first letter. This would remind, the first letter T reminds us of the tan function. It would be positive, and the reciprocal related function, which is cotan, would also be positive, because you just flip this over. So if tan's positive, cotan's positive. And everything else is negative. Just tan and cotan are positive. The word calculus, first letter, reminds us of cosine, so therefore cosine is positive, and the reciprocally related function called secant. So if these are the only 2 positive ones here, everything else is negative. So although that phrase, all students take calculus, reminds us of the positive ones, it also clues us into what's negative. But we just happened to find it right away, but I still reviewed that saying. So here we have tan is negative, sine's positive. Let's do a nice clean picture without any sayings on it. We need to be in quadrant 2. Okay, and our angle's called theta, so I'll put it there. You can put a reference angle if you want to, or you can just put theta. Okay, then the numbers, knowing where to put the numbers on the triangle, again, has to do with you knowing the formulas. Sine is defined as y, that's the numerator, over r. So your r value is 5, and your y value is 2 square roots of 6. You're looking for x, which is going to be negative. You're over in a quadrant where the x values are negative. Okay, you, as in 2 or 3 of the other problems that have happened on this same pretest, you have 2 sides, you're looking for a third side. So you go into the Pythagorean Theorem, and it goes hypotenuse squared is equal to leg squared. One of the legs is called x. The other leg is called 2 square roots of 6. So Pythagorean theorem, hypotenuse squared is equal to leg squared plus other leg squared. Okay, when you square the 5, you get 25. When the x, you don't know that yet, though you're solving for that. When you square this, you have to square this coefficient out front, the 2, which gives you a 4. And you also have to square this square root of 6. When you square a square root, it just makes the square root dissolve. Out comes the number that's underneath the radican. And then you take those two pieces, the 4 that you got from squaring the 2 and the 6 you got from this, and you multiply them together. So that would be 24. Then if you're solving for x squared, you'd want to subtract 24 here, subtract 24 here. That leaves you with 1 is equal to, because 25 minus 24 is 1. The 24s would be done, and the x squared would be on the right-hand side. Take the square root of both sides, and you get x is equal to 1. You now know that this horizontal leg is now -1. Don't forget, as I've been reminding you in every problem, the horizontal, this is all the way back to chapter 6. Horizontal leg represents the cosine. This represents the sine. Or you can think of your definitions specifically, since you don't have a hypotenuse of 1, you can think of your y and x definitions. Like for instance, if you're asked for, you can use the vertical leg as the whole sine and the horizontal leg as the entire cosine, but really only when you're in a triangle where the hypotenuse is 1. Then you can get away with that. So here let's stick to our x and y type definitions for sine and cosine that we learned in chapter 6, and I will remind you of those. Okay, right now we're moving on to the final question, which is to find cosine of 2 theta. Theta being the triangle that was built upon this theta right here. Okay, so that formula that we need, one of the ways that you could describe cosine of a double angle, it has 3 different formulas. This was one of them, and it happens to be one that we just used in a previous problem on this practice test. It went cosine squared, and whatever the angle is that they're doubling, that goes here, minus sine squared. That is one way to define cosine of a double angle. Cosine squared theta minus sine squared theta, and the theta will just be what is being doubled in here. Okay, now as far as you doing the arithmetic for this, cosine squared of theta means cosine of theta. Get the cosine off the picture and then square it. Same thing here. Get the sine off of the picture of theta, then square it. So cosine defined as, since we don't have a hypotenuse of 1, we can't just think of the horizontal leg as the entire cosine. It would be x over r, definitions from 6.1, when a hypotenuse is not 1. This would be defined as y over r. So we would have, and don't forget we're squaring them, we would have -1 over 5. That would go right there. And then we would have, for sine, which they gave us anyway, 2 square roots of 6 over 5, and we are squaring not only the cosine but also the sine. So continuing with that, we're going to have squaring the top. -1 times -1 would be 1. Squaring the bottom, you get 25. There's a minus sign. Squaring 2 times square root of 6, we had already done it down here. It came out to be 24. And squaring the bottom came out to be 25. Since both denominators are the same, you can very easily pull it into a single fraction and then combine these numerators through this subtraction sign. So 1 take away 24, -23. So that's a pretty long problem because you have to think out, since they didn't directly tell you what quadrant to spin into, you have to reason out by way of this comment right here on negativity, what quadrant you're in. You're using that comment as well as the sign that you see on this value to figure out what quadrant you're in. There were problems that only involved that back in chapter 6. And now it just keeps going. Okay, into some inverses now. I believe this started in, probably section 7.1. This would be in 7.1. And then I believe in 7.2 there was we continued with inverses, but then into inverse cosecant, inverse cotangent, and inverse secant. Inverse secant, cosecant, and inverse cotangent. So they're inverses. They're all done the same way. All inverses are equal to an angle. And you're going to want to, as soon as you realize that the value of this is some unknown angle, you're going to want to rewrite it in a non-inverse form. So switch the theta and the value, just let them switch places, and you now have a direct statement rather than an inverse statement. And so you are looking for an angle where the cosine value is square root of 3 over 2. It is negative, so you have to be in territory where the cosine value is negative. Think of that. Now we are thinking about a unit circle now with a radius of 1, because those are the only ones that are related to these special right triangles. So this is like the x value, the horizontal leg, and we have to be where it's negative. And don't forget, when you do these inverse problems, they have restrictions. I told you to memorize them by way of a picture. So the inverse restriction is this picture. When you go to do your drawing, which we're about to do, you are restricted in here with your answer. And we've done a number of reviews even in class where we practiced these pictures. Okay, if you're going to hope for anything to be negative, such as the cosine, because there's no negatives in quadrant 1, you're going to have to be in quadrant 2. So once you remind yourself of the restrictions for inverse, which is this picture right here, now draw a clean picture. Okay, we're going to be in quad 2, and we're going to put the values on the picture that you have been given here. Cosine is negative square root of 3 over 2. And you can assign that entire cosine value to the horizontal. Have these values associated with a 30, 60, or 45 degree special right triangle. They are with respect to triangles that have hypotenuse of 1. So this is the horizontal leg, which is the long leg. Therefore, this has to be the short leg. This vertical leg always dictates what the reference angle is. So, for this particular problem, this would be, the reference angle would be 30 degrees, or pi over 6. I want you to give me these in radians. Okay, so that reference angle is pi over 6. But remember, the point that I tried to stress in class was that the final answer to the problem when you're looking for an inverse is not the reference angle. The reference angle just sets you up to get the final answer. The final answer is, where is this hypotenuse? How far must one spin in order to get here? Because that's the final answer for theta. This reference angle just helps you to figure that out. Okay, so let's think. Let's count in fractions. When you spin from here all the way to here to the 1 pi location, that 1 pi can be written in terms of sixes. You could call it 6 sixes. So you really never made it all the way to 1 pi, but you should definitely, as a strategy, know what 1 pi should be called with respect to the reference angle, because that'll allow you to get this theta. So you have rotated all the way to 5 sixes of a pi, because you rotated it, but you stopped 1 6 before you got to 6 sixes. So that's subtraction. 6 sixes minus 1, the 1 6 right here is 5 sixes. So your final answer there, 5 pi over 6. Okay, then moving to number 10. Problem number 10, same thing. This is equal to an angle. You're going to write it in its direct form, in other words, in its non-inverse form, just by switching this and this. Switch spots, and you will have negative square root of 2 over 2. Before you draw your picture, remind yourself, where are you restricted to? So for inverse sine, which we're doing, that's from here to here. This is the inverse sine restriction. So your answer needs to be in here, and you are not to spin out of this region. Inverses are restricted. Okay, so if I want negatives to happen, that's never going to happen here. There's no negatives here, so I have to be down here in quadrant 4. So clean picture. Here's my spinning arm. Close it up. Put this right here on the, this is the y value, sine is the y value, in other words, the vertical leg. So that goes right here. This would be the same thing, square root of 2 over 2, and you know that that is a 45-degree reference angle. But again, stressing that you need to tell what direction and how much you had to spin to get to here, because that is the actual theta in the final answer. So if you know that you cannot spin out of this region, you may not spin like this to get to where this pink arm is. Instead, you're going to spin this way so that you're staying in this restricted zone. Not allowed to leave that. So this would be called, let's see, you'd have to spin this much right here, pi over 4 to get down here. But because you're dropping down, it is negative. And that is your final answer for that problem. Okay, that takes you through number 9. No, actually number 10. And here we are with number 11. Okay, inverse tan again. This is equal to an angle. We want to know, when do we have a tan value? For what angle do we have a tan value of negative 1? Let's remind ourselves of the inverse tan restriction. Okay, inverse tan restriction is like this. You can't give pi over 2 as an answer, and you can't give this as an answer, negative pi over 2. But you can give anything in here. So it's like the sine function, but you can't give either one of those answers. So now when you go either one of these endpoints. Okay, so now let's look at this. We know that the only way that you're ever going to get a tan value of 1 is when you're in a 45, 45, 90. So like, for instance, you see that if you were right here, this is the only place that negatives occur. No negatives occur. You have to be down here if you're going to get a negative. You'd have to have a triangle like this. Square root of 2 over 2 for one leg, square root of 2, and that way the tan would be negative 1. See, y over x would be 1, but it'd be negative 1 because of this negative right here. So that would have to be associated with a 45-degree triangle. So the reference angle is 45, and actually the same answer as the last problem. You're not allowed to spin out of this region. You're not allowed to give either of those endpoints, but you're not trying to give either endpoint. So this arm is the final answer, and you want to say, how can you spin to get to that pink arm without leaving this restricted zone? So you can't go that way because you'd be passing through these forbidden zones. This is the allowable region that you're allowed to dwell in. So again, be the same answer for this problem. Okay, number 12. You don't know how to give an exact value, and you're being asked to find an exact value for 75 degrees. Yet all you know how to work with is 30-degree right triangles, 60-degree right triangles, and 45-degree right triangles. But what you can do is you can break this number up through either a sum or a difference, which is why it's in the section called the sum and difference formulas, which you were given for sine, cosine, and tangent. So you're going to have to know the sine formula, and you're going to have to decide whether you're going to add or subtract. I think the most reasonable thing would be to add two angles to get 75, and you know one of them has to be a 45 because you are purposely trying to use anything related to a special right triangle, the 30, the 60, the 45. Okay, so you can write this as sine of, and I knew one of them was 45 just simply because this number ends in 5. And then the 30 would be the rest of it, making up the entire 75 degrees. Well, there is a formula for the sum of a sine. You have to have that memorized, obviously. It goes like this. It's got a hybrid, in other words, a mixed product in the front and a mixed product in the back. I mean a mixture of sine and cosine, unlike the cosine formulas. So when you're doing the sine of a sum, the sum of a sine, it's a mixture in the product. And the angles are what you put right here. So it's sine times cosine, sine of 45 times cosine of 30. Also in the sine formulas, whatever sign, if it's a plus in the condensed version of the formula, it's a plus in the expansion. So this will match this always in the summation sine formula. And then just like you have sine times cosine here, you're going to have sine times cosine here. Only then the angles switch. The 45 was with the sine, now it's with cosine. The 30 was with cosine, now it's with sine. And some of these values you may have memorized already, and some of you are probably still drawing the pictures. So if you are still drawing the pictures, here's a 45. Remember the sine value, which is the vertical leg, is square root of 2 over 2, as well as the horizontal leg, which represents the cosine. That's for a 45. And remember, whatever they mention here, that is the angle at the origin, right at the connect, where the y and the x-axis intersect. So if you need a picture of a 30, here it is. I would suggest you draw them whenever it's a 30 or a 60, so you don't get the short leg and the long leg, the sine and the cosine mixed up. Okay, so 30 at the origin. Across from the 30 would be the short leg. Again, vertical leg represents the sine, and the square root of 3 over 2 would represent the cosine. It would be the long leg because the 60 would be up here. Okay, so now we have everything we need to plug into this so that we ultimately find the sine of 75. But we're doing it through this expanded formula since we don't know how to work directly with a 75. Okay, so we're going to get sine of 45 times cosine of 30, and then sine of 30 times cosine of 45. So sine of 45 right here, square root of 2 over 2. So cosine for 45, I'll go ahead and put that in. Cosine of 30, horizontal leg. Sine of 30, the vertical leg. And now start multiplying. So in this first product right here, top times top, square root of 6. Bottom times bottom, 4. My handwriting is deteriorating here. And then numerator times numerator here after the plus sign is square root of 2 and a denominator of 4 when you multiply those two denominators. You can give it like this, or you can pull it together into one fraction because they have common denominators. Gives you the right to do that. So this or this, either one, no decimals. Pretty much everything on this test, with the exception of a couple of problems, are exact values. I'm not even using my calculator. Once in a while, you use the calculator to, maybe help you with some of the combining of the fractions, but literally you're getting all the values off these pictures. Although, as I mentioned before, some of you may have certain ones memorized. And that's up to you. All right, so now this actually does allow us to use a calculator, but you need to know how to use your calculator in this case. Of course, I'm not going to give you one that's just blatantly obvious where the key is staring you in the face. I'm going to give you something that we talked about. How do you handle your calculator when you're being asked to do things that you don't have keys for? So you have to know that what was stressed when it came to these particular problems is that this can be written in terms of its reciprocal. The reciprocal to cotan is tan, but still in its inverse form. So not only are you going to rewrite this trig function in terms of its reciprocal, but you're also going to do the reciprocal of this number. And that's how you allow yourself to use your calculator using the keys that you do have. Okay, so reciprocal of the number as well as the reciprocal of the function that's mentioned here that you don't have a key for. So now we're going to be able to work this in. This says do it to the nearest number of degrees, therefore your mode should be in degrees, which I reminded you of anyway. And then here I am writing it twice. So just make sure your mode is in degrees. Mine is, so I can quit out of there. Clear this and then press it in. So for number 13, it is, now I got myself using the inverse tan key instead of the inverse cotan key. So second inverse tan and put in that reciprocal. Reciprocal is 1 divided by negative 0.9347. I have it in degrees, so therefore my answer is going to come out in degrees. Rounded to the nearest number of degrees, which would be negative 47. Okay, same thing here. This is the same problem. You don't have a key for it. So think about who this is reciprocally related to. Oops, left out the I. Okay, that's reciprocally related to cosine. But still in its inverse form, we're doing inverses. And then don't forget to do the reciprocal of the number as well. Okay, now you have it in usable key form. You're in degrees already. Still says do it to the nearest number of degrees. So here we go. Second inverse cosine. And we're doing 1 divided by 5. And that turns out to be, let's see, nearest degree, 78. Okay, so that's number 14. Now moving on to 15, 16, and 17, where you are going to be solving equations. You have 3 equations that you're going to be solving. Okay, this first one is a linear equation. The next one's a second degree equation, and then the next one's a double angle. Okay, so here, when you're solving a first degree equation, you just isolate that first degree term, removing any numbers that are added or subtracted first. So let's add 4 to both sides, and this will be 2 times sine of x is equal to 1. Divide by 2, and you get sine of x is equal to 1/2. You are looking for the angle, just happen to call it x, sometimes they call it theta. You're looking for the angle, called x, where the sine value is 1/2. You can be anywhere in between 0 and 2 pi. So you don't have little pictures that represent restrictions. Those are inverses. Here, they tell you that you should only give answers between 0 and 2 pi. Okay. So what we're going to do here now is say, okay, I want my sine value to be positive. Remember, the sine is like the y value. And if I want my sine to be positive, that means I can actually be in 2 different quadrants. Here y values are positive, and here y values are positive. Okay, go down to the x-axis, close up these triangles, and put this value where it belongs. The sine value is always the vertical leg. So that goes here as well as here. And then if you have the vertical leg is what tells you what the reference angle is. Always across from 1/2 is 30 degrees, which is pi over 6. And if that's the reference angle here, all the reference angles are pi over 6. So again, remember, just like when you were doing inverses, the final answer is not the reference angle. It is where the hypotenuse is. So you need to tell where that is, and you need to tell where that is. There are two solutions to this problem. So in quadrant 1, the theta is always the same as the reference angle. But in all the other quadrants, that's not the case. So this is one of your answers. And then this will be my other answer right here. But here you got to think a little bit more. But we've done this quite a bit. This is the 1 pi location. In terms of sixes, that's 6 sixes. So if you're rotating here and you stopped 1/6 before you got to 6 sixes, you're at 5 sixes. And that is the second answer. So you can give your answers in a solution set. Or you can just separate them by commas. That's fine also. I'll just be thrilled if you get the answer. Okay, then we come to now second degree type equations. And there are various ways, as we discussed in class, for solving second degree. Since there's no term in this problem to the first degree, it's only a second degree term and constants. So since that first degree term is missing, you can use the square root property. If that wasn't the case, we'd have to factor. If we had a squared term, a first degree term, a linear term, and also a constant, then we'd have to factor. But because that first degree term is missing, we can use square root method, but don't take the square root until you've isolated the square term. So in other words, divide off that multiplier here as well as here. That'll get you sine squared. Theta is equal to 3/4. Okay, now you can take the square root once there's nothing else on the same side as the squared term. And you can take the square root here. Don't forget, second degree equations have two answers, and this plus or minus will allow you to get those two answers because you're going to be looking for anywhere that the sine, because square root of sine squared, this square root dissolves the square, so now you're just talking about just sine. We're looking for either the positive or the negative version of this square root. So the top you can't take the square root of, it's just 3. And then the bottom you can take the square root of. And you recognize that. We work with this number all the time as a sine or a cosine value. So we can be where the sign is positive. Again, this is like the y value. Or we can also be where the sign is negative. So we can literally be in any of the 4 quadrants. Okay, in these top 2 quadrants, that's where the sign is positive. Because again, the sign is like the y. So y's are positive up here. So we can be up here. Or we can be down here where the signs are negative. Okay, so let's put this value where it belongs. The sine value is the vertical leg. And you're down here where the y's are negative, and put a negative there. Okay, and it's perfect because the vertical leg actually tells you what the reference angle is. So the reference angle is, let's see, always across from this square root of 3/2, which represents the long leg in that long leg, short leg scenario, is the 60 degree angle. So that's pi over 3. And if this reference angle is pi over 3, all of these reference angles are pi over 3. And then I cannot stress it enough that ever since chapter 6, I've been trying to bang in the difference between reference angle and real theta. The real theta is where the hypotenuse is. So you got an answer here, an answer here, an answer here, and an answer here. And all these answers are going, well, 3 of them specifically, are going to have to do with your ability to name the landmarks on this circle, if there was a circle drawn here. Like for instance, by the time you get here, this is known as, by the time you rotate halfway around the circle, this is known as 1 pi. Since we're talking thirds as dictated by the reference angle, this is 3/3. So some of these arms that you are looking for a solution for, some of them will stop before they get to 3/3. Some of them will go beyond 3/3, indicating either addition or subtraction of the reference angle. This over here, well, this is 1 pi, so 2 pi would have to be 6/3. 6 divided by 3 is 2. So these are your landmarks, this and this. And you're going to judge, am I stopping before I get to a landmark? Because if you are, you have to subtract the reference angle. Or am I going beyond the landmark? Then you have to add the reference angle. Okay, as stated in several other problems, in quadrant 1, the reference angle and the actual theta and its associated theta are the same. In quadrant 2, 3, and 4, that's not the case. So let's see, if you were rotating to get to this pink arm in quadrant 2, but that pink arm stopped before it got to 3/3, and this is, it stopped before it got there, 1/3, so 3/3 minus 1/3, 2/3. Always subtracting if this arm stopped before it got to the landmark. However, if you're going to continue rotating until you get here, this pink arm is past the landmark, indicating that it is more, that it has rotated further than 3/3. So this would be, and how much more? It went this much further beyond the 3/3. So it was like you rotated to 3/3 and then went an extra 1/3. So this represents 4/3. Okay, final answer. I'm just putting little subscripts in here just to name the angles, not that you have to. And then here, I'm on my way, rotating, on my way to 6/3, but never quite made it there. This is the 6/3 mark, right when you get back to the 0 point, or what's also called 2 pi. So this pink arm, this last pink arm, stopped 1/3 before it got there. So this one is at 5/3. And so your solution set is 1/3 pi, 2/3 pi, 4/3 pi, and 5/3 pi. With the pi's always at the top. Last but not least, and I may have to run off into other paper here, is how to solve when the angle is a multiple of something. Now, what I'm going to do, as you saw in the lecture notes, it can be done if the angle is 3, 4, 5. I mean, I'm not going to run you past 2. That'll be enough for you to deal with, but it can also be done if it's a 1/2 or a 1/3. I'm just going to give you, I'll probably give you the double angle. Okay, so no double angle formulas, because then if you start throwing in the double angle formulas, you're just going to make this problem even more complicated. You don't want any more than one trig word in this problem. So I'm going to suggest that you just stick with what you have here and learn what the procedures are for you to ultimately find out what this solution is for a double angle. First of all, I would start by just ignoring the double angle. In other words, I would pretend as though what you're looking for is just where is the cosine of some angle. Don't worry about it being a double angle. Where is it equal to square root of 3/2? First, just see if you can figure that out. You see that this is a positive value, so you're looking for where cosine is positive. So that means, now you can, they say that you can be anywhere between 0 and 2 pi, but let me tell you what the doubling of the angle does to that allowable interval. They say that you should only find answers between 0 and 2 pi, But when they say you can double the angle, that means you can double these endpoints on this interval. Because these are angles in here. And they're saying that you can double that. So this is actually called the domain. And it has the effect, the impact of doubling that interval. So you are now allowed to find answers. Let's double everything here. Let's double this. 2 times 0 is 0. And 2 times 2 pi, I'm just multiplying. I'll just put a little dot there. 2 times 2 pi is 4 pi. You can find solutions anywhere from 0 to 4 pi. That means you get to spin around the circle more than once. Okay, you can spin around the circle twice, finding as many solutions as you can where the cosine is equal to square root of 3 over 2. Remember, you need to be in territory where the cosine is positive. So this would be the first place. This is cosine. Remember, that's like the x value. Cosine's positive here. Cosine's positive here. Okay, close up. Put this value where it belongs. Cosine is always the horizontal leg. Let's see if I can move that over a bit. So I can put the reference angle in there afterwards. So square root of 3 over 2 right here for this horizontal leg. And I'm just going to mention it once because this horizontal leg belongs to the upright triangle as well as the upside down triangle. So if this be the horizontal leg, then this has to be the vertical leg. And the vertical leg tells you what the reference angle is. That reference angle would be, let's see, always across from the 1/2. This is the short leg always, the 1/2 value. Therefore, this has to be 30 degrees, or what we call pi over 6. Okay, let's see if I can make this just a little bit bigger. Maybe. Okay, so you can see my reference angle is pi over 6. But if this angle is pi over 6, then so is this one. So one of your answers right here, this would be theta is equal to pi over 6, because in quadrant 1, theta matches the reference angle. But over here, if you had spun all the way from here to here, we're thinking sixes. This is 6 sixes. This is 12 sixes. Because remember, this is called 2 pi or 0 degrees. So if you were rotating on your way to 12 sixes but never quite made it there, and this is how much you stopped before getting to 12 sixes. 12 sixes, you stopped 1 6 before getting there, so this would be 11 sixes. But you are allowed to spin around this triangle more than once, because the domain, because of this right here, because they doubled the angle in the answer, it also doubles this entire domain, the allowable domain through which you're allowed to spin. So if you want to get 2 more answers, but still landing exactly where you are now, because you already have figured out that you need to be in quadrants 1 or 4 in order for the cosine to be positive. You already know the thetas that are associated with the reference angle. You figured out that this was 1/2 because this was square root of 3 over 2. That gave you the pi over 6, which gives you this solution and this solution, but there's 2 more. If you want to spin, let's say you're standing on this solution, the one at pi over 6, and if you want to land on this arm in chapter 6, you could just rotate a full 360 degrees and land right back on this arm again. In that way, you have spun around twice, exhausting all possible solutions, but forcing yourself to land in the very same place that these arms are drawn right now. So another answer that would go with this would be pi over 6 pi. If you can't handle that in your, do that in your head, then you should just delete it. You're just adding 1/6, 1/6 of a pi. Don't put the pi in your calculator, just 1/6 plus 2. So you just go 1 divided by 6 plus 2. Math key in the first column. Enter, enter. There you go. 13/6 is what you get. Okay, let me go back down to a smaller window here. So when you go 1/6 and then you do a full rotation to make yourself land here again, this would be called 13/6 of a pi. So you have, now these solutions, I want to point out that these solutions, pi over 6 and 13 pi over 6, these are semi-solutions. They are not the full finale of the solution. Okay, also don't forget this arm down here in quadrant 4. This is the first time we spun into quadrant 4. Make yourself get in quadrant 4 again, landing right here. So imagine yourself standing here at 11 pi over 6. You're going to rotate a full 360 and make yourself land right back in that same spot because you're allowed to rotate more than just one time around the circle. So here I am rotating the second time, but making myself land right on 11 pi over 6. So the other angle here would be the 11 pi over 6 I started on, plus a full 360 rotation, which is the same thing as 2 pi. If you need help with that, just put in the coefficients of the pi, the numbers in front of the pi. 11 over 6 plus 2. 11 divided by 6 plus 2. Math, enter, enter. 23 over 6. And that is a pi number. Okay, now many students would be tempted to give these answers. But if you take these answers and plug them right in there, they are not going to give you square root of 3 over 2. So there is one final alteration that you need to do. These are semi-solutions. Okay, and you're going to use these to get the final solutions, which I'll finish on the back. Use these to get final solutions. Okay, on the back, you're going to see me figuring out what this has to be with respect to 2x. If you want to know what you could take the cosine of and get square root of 3 over 2, make this equal to each one of these angles to get each of the 4 final solutions. So we have a pi over 6, an 11 pi over 6, a 13, and a 23. I'm going to finish that on the back. You're going to be using each of these angles set equal to 2x to get the final answer. Okay, 2x equal to pi over 6. We'll solve that and get one final answer. And then we also had a semi-solution of 11 pi over 6. We also had a semi-solution of 13 pi over 6. And we also had a semi-solution of 23 pi over 6. Okay, so what we're going to do here is solve for x. So divide by 2. Dividing by 2 is the same thing as multiplying by 1/2. So you can do it this way on this side just for convenience. But on this side, because it's a fraction, instead of dividing by 2 and then floating and flipping, just know that division by 2 is the same thing as multiplying by 1/2. So you're actually doing the same thing on both sides. So one of your final solutions, pi over 12. Not pi over 6. So in the end, very last step, you need to work that multiple angle, whatever it be, but it's probably going to be a 2x, with the semi-solutions that you have. So I have one answer in its final form. Here this would be 11 pi, top times top, over 12. Here's another one. So 13 pi over 12. Okay, so here it would be 23 pi over 12. Okay, and those are your 11 pi over 12, 13 pi over 12, and 23 pi over 12, which you can give in a set, or you can just list them separately and separate them by commas. That is the finale of this practice test number 2, which is very similar to the real test. So make sure you do it as many times as you need to in order to memorize all the formulas. Okay, good luck studying.